Hi, my name is Eric Siniceros. I work with Henry Fu in the Mechanical Engineering Department. I'd like to tell you a little bit about what our research group does in general and then how I'm contributing to that effort. There's a lot of modeling of microscale hydrodynamics of biological organisms, so E. coli swimming, sperm swimming, things like that. And my purpose is to create an experimental environment to test these models in. We can get samples of these biological fluids and the organisms and view them under a microscope, but we cannot measure forces without interfering with that environment, right? So what we're using is photoelasticity of a couple of materials, gelatin and alginate gels, to try and make an environment where we can actually visually see the forces that these organisms are exerting. Just to get a show of hands, who's heard of photoelasticity before? That's two more than I expected, honestly. So our apparatus looks like this. We have a polarizer, a linear polarizer. I can't spell very well. Light source. Our sample in the middle. And then a polarizer that is 90 degrees opposite of this. And that's a phase angle of the light, right? And then we have a camera to view this. So certain materials called birefringent materials will shift the polarization of light when put under strain. So this is very common and has been used for 50 years in solid mechanics to view stresses around bolts and things like that. Polymers all do this. Our materials, gelatin and alginate gels, also do this. So what we're measuring with the camera is the shift in the polarization of the light source. So far, we've been able to make beads of gelatin down to about 200 microns. We don't have the equipment to view those yet, but we made them. And right now we're working with beads that we can view that are about 2 millimeters in diameter, and we're working with earthworms and things like that. So in addition to modeling these microscopic environments, making these microscopic environments, another big application is with nematodes. Nematodes were the first organism to have their genome completely sequenced. They're very scientifically relevant for genetics research and neurological research because they're very simple. They have 6 motor neurons that you can zap with a laser and kill off the ones you don't want to study. There's been a lot of work recently to determine the minimum, input threshold that will instigate a response in these neurons. Most of the work is with a PDMS tower right now. Sorry, I'm getting kind of big on the board here. So people will make a tall, skinny tower out of a PDMS material with a target on the top. And you know the Young's modulus of this and the length. And you can view it with a camera, and when the worm touches it, it'll deflect, and you can determine the force. And they haven't been able to determine the minimum force required for a response with this technology. We're hoping to put, in addition to that, they have a lot of other kind of blank towers for the worm to work with, which isn't, you have a lot of contact points that you're not taking data samples off of, right? So we're hoping to make a fully natural environment, for this nematode to move through and measure the forces that it's exerting on its environment very precisely so we can determine the minimum response. And I'll take any questions if you have them.
How can you know that you have a 200 nanometer whatever thing if you can't see it?
Oh, that's a good point. I should clarify that. We can see it under a microscope, but we don't have a photoelastic setup with the polarizers to see the polarization change yet. So we can see that we've made them, but we can't tell if they're even photoelastic yet, to be honest.
Why did you choose gelatin and
It's so the photoelastic effect is linear with strain on the object. Gelatin, first of all, it's cheap. It's the same thing that's in Jell-O, right? And it's soft, so there's a high strain rate, so we can get a higher sensitivity, hopefully.
So are your nematodes or whatever moving along the top of the surface of the gelatin or through some sort of a three-dimensional medium?
We haven't gotten to nematodes yet, but our earthworm-sized things, we have worms that are smaller than that too. They're moving through a two-dimensional bed of spheres, essentially. Interesting fact, there's a huge variation in the quality and the mechanical properties of gelatin. The highest quality and best place to go for that is actually the people that make Jell-O and buy it off the store shelf at Raley's.
So you choose that material that's similar to original biological system?
That was a factor in our decision too. Gelatin's been used for determining the forces around a colony of bacteria, millimeters in size, so we know it's biocompatible. You can also treat it with formaldehyde or glutaraldehyde, which cross-links the proteins and makes it non-water soluble. It's the same process you use to preserve, rats and snakes and things in jars in biology class.
So while measuring the force exerted, do you account for the material properties like the elasticity, softness, because some of the force being absorbed during impact?
Mm-hmm. Let's see. I guess we're not directly measuring the force. We're measuring the strain in the object, in the sphere. And that's what produces the photoelastic effect. So how we're calibrating the system is directly from force to the light signal observed by our camera. There's no intermediate steps. We're not determining the Young's modulus or any of those other properties of the material. We're kind of cheating to get around that. All right, thank you for your time.